In the last lesson, we looked at an overview of the different pins on an Altera CPLD, the EPM3032A. In this lesson, we're interested specifically in the I/O pins, which you see highlighted in green, because each of these pins can serve either as a digital input or a digital output. There are many different types of digital logic levels, for example 5-volt TTL and 3.3-volt LVTTL. If we take a look back at the datasheet for this EPM3032A CPLD, it has a multi-I/O interface section that describes how inputs and outputs can follow plus 5-volt, 3.3-volt, or 2.5-volt digital logic levels. For each of those cases, it would mean that 0-volt is a logic 0, and either 5-volt, 3.3-volt, or 2.5-volt would be a logic 1. The EPM3032A achieves these different I/O settings by using two different types of power signals, VCC-IO and VCC-INT. So this device has one set of VCC pins for internal operating and input buffers called VCC-INT and another set for I/O output drivers, VCC-IO. To see which pins on the CPLD are VCC-INT and VCC-IO, the datasheet recommends to go to Altera's website and use their pinout documentation. When we do that, you can see their PDF file shows that VCC-INT are pins 17 and 41, and VCC-IO are pins 9 and 29. Scrolling further down, we can see a full listing of all I/O pins and which logic array block or lab they belong to. There's a lab A and a lab B for this part. So in reality, the EPM3032A CPLD is split in half, with two logic array blocks that can communicate with each other, but can be set to different user I/O logic levels. But throughout this course, to make things easier, we will always use 3.3 volt on both VCC-INT and VCC-IO. So let's move on and build up an example project to use an input to drive an output. To start the theory section, first we'll create a new Altera Quartus 2 project. Choose where you want to save your project. I'll save mine in a folder on the desktop called FPGA Lesson 3. Then type in the name of the project, Lesson 3, and click Next. Here we need to choose the device that we're using. Again, it's the EPM3032 ATC44-10. Then click Continue and finish the project creation. Since our Lesson 3 project doesn't have any files at the moment, we go to File, New, and click on VHDL file to add one to our project. Like last time, first we need to declare the IEEE libraries that we need to use, specifically the standard logic libraries. Then we need to create our top-level entity. This time our port is going to have an input called button 0 located at pin 23 and an output called LED 0 located at pin 22. Moving on, we'll name our architecture RTL, and it will have only one line inside of it telling the CPLD that LED 0 should be driven by the input button 0. Then save the file as lesson3.vhd and compile the design. After the compile finishes, go to the Assignments Pin Planner and make sure that button 0 is assigned to pin 23 and LED 0 assigned to pin 22. Then go ahead and compile the design again. At this point, the pins for the location and fitter location should match. So now we have a project that sets pin 22 to whatever logic level is at pin 23. If a logic 1 is at pin 23, then pin 22 should output a logic 1. Next, we need to build up the hardware schematic to go with this project. First, we build a power regulator circuit. It consists of a 9-volt battery going to an LM317, an input bypass capacitor of 10 microfarad, along with two resistors that set the output voltage of the LM317 to 3.3 volt, then a bypass capacitor on the output plus 3.3 volt, along with a resistor and LED for notification that power is good. The CPLD connections begin with connecting all VCC pins to plus 3.3 volt and all ground pins to GND ground. Then pin 22 connects to a resistor and LED to be turned on or off, and pin 23 connects to a push button with a pull-down resistor going to ground on one side and a connection to 3.3 volt on the other side. So when we load in the code from the Lesson 3 project, pin 23 is a logic 0 initially, so the LED connected to pin 22 should also see a logic 0, and it will be off. But when the button is pressed, 3.3 volts will be present at pin 23, so pin 22 should change to a logic 1 and output 3.3 volts to the LED, turning it on. To start the experiment, first we'll go through all the parts necessary to build up the circuit. The larger parts are a jumper wire kit, components kit, and a breadboard. The specific parts from the components kit are the CPLD breakout board, LM317 voltage regulator, two 10 microfarad capacitors, two 470 ohm resistors, a 390 ohm resistor, a 240 ohm resistor, a 10 kilo ohm resistor, two red LEDs, a push button, and a 9-volt battery connector. To build the circuit, we first need the breadboard, then we'll use two orange jumper wires to connect the power and ground bus lines together, and then we'll connect the 9-volt battery connector to the breadboard. Next, we'll build the power regulation circuit. The LM317 is placed into the breadboard along with two resistors to set its output voltage. Then two bypass capacitors are added onto the input and output. And finally, we add an LED and a 470 ohm resistor from power to ground, completing the voltage regulation circuit. Place the CPLD breakout board at the opposite side of the breadboard. We'll use yellow wires to connect all of the VCC pins to the red power bus, then we'll use dark green wires to connect all of the ground pins to the ground bus. A 470 ohm resistor connects from pin 22 to an LED that connects to ground. And finally, we place the push button into the breadboard, connect one side of the button to pin 22 with a white wire, and the other side to 3.3 volt power, and then finally add a 10 kilo ohm pull-down resistor which connects to ground. Now a circuit is ready. Get your JTAG programmer, 9-volt battery, and laptop with the Lesson 3 project ready to use. And first we'll connect the 9-volt battery to the circuit to power it up, then connect the JTAG cable to the breakout board, and finally connect the JTAG programmer to your laptop. Open up the Lesson 3 project that we built earlier in Quartus 2 and double-click Program Device. Add the .pof file from the Output Files folder, then check the Program/Configure box and start the programming process. And as you can see, when we press the push button, the LED turns on exactly as expected. Let's make a quick modification to the code to prove we have full control of what's going on. Right before button 0, add a NOT, N-O-T, which would be exactly the same as adding a 7404 NOT gate to invert the logic. This will make everything opposite, so when a logic 0 is input from the button, a logic 1 will be output to the LED. Then save and recompile the design, and when it's finished, reprogram the CPLD with the newly generated image, and the idle state now has the LED on, and when we press the push button, it turns the LED off. So everything is backwards, exactly as we expected, since we put a NOT gate in between the input and output. In the real world, there are countless different forms of input and output voltage levels, from 5 volt, 3.3 volt, 2.5 volt CMOS to PECL and LVDS. All of these have different specifications to work properly, and you should be aware of whether or not your device can handle them. For example, our EPM3032A CPLD can only output 3.3 volt or 2.5 volt CMOS logic on two different logic array blocks. In contrast, an Altera Cyclone 4 FPGA has many I/O blocks or banks, with each one able to output different CMOS standards and differential pair standards, making the FPGA the real king of user I/O and the CPLD merely entry level.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Next time, we'll take a look at how to implement combinatorial logic in a CPLD by moving from Boolean algebra to VHDL code.